Good afternoon, Professor. Okay. Good afternoon, Professor Boyle.
Good afternoon.
This
Yes,
is Symmetry here. Hi.
Hi. Hi, Assam.
So I think we are ready to start.
Okay.
You can
Go ahead.
start at a little bit slower pace and then pick up because people are joining and I'm allowing them to join.
Okay. Okay. Would it would it make sense to give maybe 1 minute just to give if I see people are still coming in at a relatively
That's right.
relatively high pace, so I just don't want to leave them behind. Okay, great. I will share my screen here. And get started. Okay, you can see my screen now, is that right?
Yeah, it's coming. It will take a little bit of time. Yeah, I can see it.
Okay. Okay, very good. So welcome back to lecture 2 about the application of group theory to the standard model and beyond. So here on the first slide here, I just wanted to briefly recap where we got last time and then introduce a new bit of notation that will be useful for us in this lecture. Okay, so here is, the summary of the first lecture was that the fundamental laws of physics as we currently understand them, that is to say the standard model of particle physics, are almost all about symmetry. That according to the modern understanding, the way you specify the standard model of particle physics is you start by choosing a gauge group, and observations seem to have told us that the correct gauge group for describing the universe that we see so far is SU3 times SU2 times U1, drawn in the top row of this table. And then to make those, the idea is that the theory is a gauge theory, meaning that those symmetries are symmetries that the Lagrangian or action that describes the laws of nature is invariant not under a global symmetry, SU3 or SU2 or U1, but under a local symmetry, a symmetry where you can choose a different element of SU3 times SU2 times U1 over each space-time point. And even when you do that, the action is still invariant, so that's a local or gauge symmetry. And we saw last time that in order to write down a theory that had that property, we needed to introduce corresponding gauge fields, which I'm calling here G mu, W mu, and B mu. These are the gauge fields corresponding to the strong, weak, and hypercharge forces, respectively. Okay, so much for the gauge fields, but then what are the matter fields in the theory? Well, to specify them, we have to specify what representation they transform in under the standard model gauge group. And it was Wigner in the early days of quantum mechanics who had the idea that the different fundamental particles of nature are nothing but the different irreducible representations of the fundamental symmetries of nature. And so, in particular, this table shows all of the different fundamental particles, all of the different irreducible representations of the gauge symmetry group of the standard model that that appear in the standard model. All the particles we know about so far. And so, in particular, here we have the first 6 rows here are the spin 1/2 particles. Okay, so these guys are the so-called spinor fields. And so we have 6 rows. We have the left-handed quark doublet, the right-handed up quark, the right-handed down quark, the left-handed lepton doublet, the right-handed neutrino, and the right-handed electron. What? By the way, when the gauge fields at the top here, as I've shown on the left, are spin 1 particles, and that more technically means that that under the Lorentz group, they transform as for those of you who have met the representation theory of the Lorentz group, they transform under the 1/2 representation of the Lorentz group. If you haven't met that, that's no problem. Meanwhile, the spin 1/2 particles down here, for the spinor fields, they transform as well, it depends exactly which representation they transform as, depends on whether they have the label L or R. The left-handed fields, which have a subscript L, transform as the 1/2 0 representation of the Lorentz group, and the right-handed fields, which have the subscript R, transform as the 0 1/2 representation of the Lorentz group. And then finally, there's one last row of the table. We saw one last matter field, which is not a spinor field, which is not a spin 1/2 field. It's the spin 0 field at the bottom, which transforms, in other words, it transforms as the 0 0 or trivial representation of the Lorentz group. In other words, it doesn't transform under the Lorentz group. And that's our scalar field to Higgs here. So the top, and then on the right-hand side here, I've just reminded you of some of the terminology that's used to describe these fields. The fields in the top row with spin 1, those are called the gauge fields. They mediate the forces in the Standard Model. And then the first 3 rows below that, the first 3 fermions, the fermions that do transform non-trivially under SU3 in the first column here, those are called the quark fields. And then the next 3 rows are called the lepton fields. Those are the 3 fermion fields the 3 spinor fields that don't transform under SU3. They don't feel the strong force. They transform trivially under SU3. And then finally, in the last line here, this guy, the scalar field at the bottom, is called the Higgs doublet, and it's responsible for the so-called quote-unquote Higgs mechanism or spontaneous symmetry breaking in the Standard Model of particle physics. And here I've mentioned that the quarks and leptons, the spin 1/2 fields, are the so-called fermions in the Standard Model, whereas the fields on the top and bottom, the gauge fields at the top and the Higgs field at the bottom, are the so-called bosons in the Standard Model. Anyway, that's just terminology. Now, so in the bottom half, so fine. So the top half of the page, above the squiggly lines here, is just to review what we found last time. So this table summarizes everything you need to know in order to write down the Standard Model Lagrangian. This table really says it all. If I tell you that the theory is a Yang-Mills theory, a gauge theory, and that these are that the matter content is summarized, the gauge group and the matter content is summarized by this table. Now, in principle, you have all the information you need to write down the Lagrangian of the Standard Model, or in other words, the action functional of the Standard Model, the formula from which you derive everything else about the model. It's just the most general formula you can write down, whose variables are these fields appearing in this table, and which is invariant under the gauge group SU3 times SU2 times U1, and also invariant under the Lorentz group and under space-time translations, under the Poincare group of space-time symmetries. Okay. And in fact, I would just recommend, due to time, I'm not going to work out what that formula is here. I will work it out. You know, that's something that's an important part of what I work out in my course on the standard model that I mentioned in the previous lecture. And that so if you want to know more about that, you know, you're welcome to look at the videos of that. Either there, I think videos of previous years of that course, by the way, are available on the website persa.org if you want to know more about that. And then this year's version of the course, I will be the sort of pandemic version of the course I'll be posting to YouTube in a few months. Anyway, so now I just, in the bottom half of the page here, I'm just introducing a new notation for the, really just, it expresses this section here expresses the same information as this section here. I'm just re-expressing that part of the table, the fermionic part of the table, in a different notation. So instead of in the first line here, in the first row of the table, where I wrote, where I said that Q left transforms as the three-dimensional representation of SU3, the two-dimensional representation of SU2, and with hypercharge 1/6, I've rewritten that down here by saying that it transforms in the three-dimensional representation of SU3, the two-dimensional representation of SU2, and with hypercharge 1/6. Well, okay, so here, this meant the three-dimensional representation of SU3. I'm using the notation here is that C3 means just the three-dimensional complex vector space. This is the vector space corresponding to the three-dimensional representation of SU3. This is the vector space on which the 3x3 unitary matrices act. Here, C2 with a superscript 2 denotes the two-dimensional complex vector space on which the 2x2 SU2 matrices act. Now here, the subscript is no longer the dimension of the vector space. This is to denote the hypercharge. So U1 acts on a one-dimensional complex vector space, and it just acts by multiplying that vector space by a phase, by a complex phase, e to the I phi. But I've just changed notation here. So not only am I writing the hypercharges as subscripts, but you'll notice I've multiplied all the hypercharges by 6 when going from the table downwards. So up here, I had a hypercharge of 1/6, but I multiply that by 6 to get this hypercharge of 1. Up in the second row of the table, I have a hypercharge of 2/3, so I multiply that by 6 to get a hypercharge of 4 here for the right-handed up quark. In the table, I had a hypercharge of -1/3, so I've multiplied that by 6 to get a hypercharge of -2. So it's just a convenient change of notation that I'm now going to multiply all of the hypercharges by 6 to, so you know, in the table, these are the conventional hypercharges used by physicists. But for the purpose of today's discussion, it'll be convenient to multiply them all by 6 to turn them all into integers. It'll just make our life easier and clearer. Okay, so I hope it's clear that these six rows at on the lower left-hand side of the page are just a translation of these 6 rows in the table. And meanwhile, over here, well, I've also included now the fact that every time we have a particle in the standard model, like the left-handed quark particle here, that we also have its in quantum field theory. We always also have its corresponding antiparticle, and that's described by the complex conjugate. That transforms in the complex conjugate representation under the gauge group, turns out. And so I've added that's what I've called Q left star here. So for every yeah, for every representation on the left-hand side, which was described in the table above, there's a corresponding charge conjugate representation on the corresponding complex conjugate representation on the right-hand side, which is the star of that representation. Okay, and now finally, in the very bottom line, at the very bottom here, I've taken these fields. I've taken my so up in this component of the page, I have 12 different irreducible representations, 12 different component vector spaces, and I'm going to split them into two parts as follows. I'm going to take all the left-handed guys and sum them and call that vector space F, okay, at the bottom here. So all the left-handed representations, well, Q left is a left-handed representation, U right is not, but its antiparticle, U right star, that is a left-handed. That does transform as a left-handed field under the Lorentz group. So I've included U right, so I've taken Q left here because that's left-handed. U right is not left-handed, but its antiparticle is, so I've included U right star down here. Same with D right. It's not left-handed, but its antiparticle is. And then L left is left-handed. Nu right is not, but its antiparticle is. And E right is not, but its antiparticle is. So that's why everybody with a right subscript has a star in this expression. And then F, so that's what F, so F is all the left-handed particles. F star are all the corresponding right-handed particles. So I just star everything to convert the expression for F to the expression for F star. So F, if you count up how many dimensions the vector space F has, you'll see that it has 16 complex dimensions. For example, Q left here has 3 times 2 times 1 equals 6 complex dimensions. And then U right star has 3 times 1 times 1 complex dimensions. So when I add those, I would get 6 plus 3. Anyway, if you add up all of these guys, you get a 16 complex dimensional vector space, and here you get another 16 complex dimensional vector space. So if you take the sum F plus F star, this sum over here, you'll see that's a 32 dimensional complex vector space, and that is the vector space of a single generation of standard model fermions. And now, if you ask for the whole standard model, well, actually, as I mentioned the previous time, for some unknown reason, there's 3 copies, there's 3 generations, there's 3 copies of this structure. So the full set of fermions in the standard model live in a 32 times 3 equals 96 dimensional complex vector space. But for this lecture, we'll be focusing on 1 generation at a time. Okay. So,
excuse me.
Yes.
How did we take the complex conjugation? Like QL star is given by C3 stars across C2 star cross C, right? Why not C star there? Why didn't you?
Oh, yes. Thanks. So let me explain that on the next page. Good question. Okay, so let's say that I have an element of SU3. Okay, so let's say that U3 is an element of SU3. So U3 is a 3x3 unitary matrix, meaning that it satisfies unitary, I remind you, means that it satisfies U3 dagger is equal to U3 inverse. And then it also, because of the S here, it's the special unitary group, so it also has determinant 1. Okay, so a representation means for every element of the group here, I map it to a matrix. Well, in this case, there's a trivial mapping I can do, which is that this thing is already a matrix, so I can map it to itself. So if I if I take the representation where every element U3 of the group SU3 is represented by a 3 by 3 matrix, which is nothing but the element I started with, I'll call that the three-dimensional that's the so-called fundamental or three-dimensional representation. And so I'll write that, a particle physicist might write that as that representation as 3, and then in my new notation that would be called C3. Now, however, there's another representation which is not equivalent, which is that I take my original element and I map it to the complex conjugate of this matrix. The matrix that I represent it by is the complex conjugate of the original matrix I started with. That's also a representation of SU3. That also preserves the product in SU3. That representation is what particle physicists would call 3 bar, and what in my notation on the previous page I would call C3 star. Okay, so for any group SUN, for any group SUN, that's the notation those are the two kind of notations that one uses. I mean, here I've done SU3, but it's obvious how that would generalize to SUN. And so in particular, when I'm talking about SU3 and SU2 today, and SU5 later on, that's the notation that I'll be using one of those two notations. Now, U1 is a different story. U1 is not one of the groups SUN, and it has a different notation. So U1 is the group of complex phases. So these are an element of U1, is a complex number of the form e to the I phi, where phi is a real number. So it's a point on the unit circle in the complex plane. So let's call this alpha. So now a representation of this would be to map this guy. I could, let's say I took the element alpha from U1. Well, a representation of it would be alpha to the p, alpha raised to some power p. That would still be a representation of the group U1. That mapping preserves the product, and that alpha to the p acts on a one-dimensional vector space. So if let's say V is an element of my one-dimensional vector space. So V is just it's a vector space with only a single basis element. Then under this representation, it gets mapped to alpha to the p times V. Okay, so in standard particle physicist notation, I would, like in my table that I started with at the top of the previous page, I would refer to that representation by the quote-unquote charge P. Okay, so that's when I had this table, when I had 1/6, 2/3, minus 1/3. That number is the exponent here. But in my other notation, I'm referring to that as C subscript P. Okay, and there was this business where I multiplied everything by 6 to turn fractions into integers, but that's irrelevant. I mean, that's hopefully that's a detail that we don't need to focus on. Now, let's talk about the complex conjugate representation. In this case, here, if we take the complex conjugate representation, it means we're multiplying. We're taking alpha. Sorry. We're taking alpha. The complex conjugate of this is alpha star to the p, which of course is nothing but alpha to the minus p, because this is just a complex, because alpha is just a complex phase. So in a physicist notation, that would be the representation with charge minus p. And in the more mathematical notation, in the lower half of the previous page, I would refer to that as, instead of referring to it as CP star, I just refer to it as C of minus P. Okay, so if we go back to the previous page, you'll see here when in the top row, for example, when I go from Q left to Q left star, I take the complex conjugate of the first two factors according to the notation I just described. In other words, the first two factors refer to the fact that the antiparticle of Q left transforms as the 3 bar and the 2 bar. And the final factor, you'll notice that what's changed is that the subscript was a 1 on the left-hand side, but it's become a -1 on the right-hand side. Okay, does that make sense?
Yes, sir. Yes.
Okay. Okay, great. So now that's all notation. Let me now just explain what's the punchline I want to get to today. And again, I have to say that as with the previous lectures, because I kind of want to get across the gist of the punchline all in one lecture, you know, I have to go a little bit. It has to be a little bit sketchy, the presentation. I'm not going to be able to work out. I'm not going to have time to work out all the steps. And so, but I'm trying to sketch enough that hopefully maybe you'll be able to figure it out on your own. And then if you want a more pedagogical presentation, or at least you'll get the general idea. And then if you want a more pedagogical presentation, you could look at my previous versions of this. I did a previous version of this course on the Perimeter Institute video archive website, www.persa.org, and then there'll be these YouTube lectures. Okay, so what is the punchline I want to say? Well, so I want to introduce the idea of grand unification as it was discovered. You know, in my opinion, there was a clear, important hint about the structure of the Standard Model, which was discovered in the 1970s, shortly after the Standard Model itself. It has to do, so what's the idea? Well, so we have seen that the symmetry group of the Standard Model is SU3 times SU2 times U1. Now, for reasons that I don't have a chance to explain here, but that you may have heard about, and that, again, you can learn about in my course or in other places, you know, at low energies, this is not the symmetry group we seem to see in nature. Instead, there's this phenomenon of spontaneous symmetry breaking. And so the group that we actually see, that we seem to see at low energies, is just a subgroup of the full Standard Model gauge group. So the one we see at low energies is just SU3 times U1. We just see the symmetry of the strong force and the U1 which corresponds to electromagnetism. We don't see this full gauge group. It seems to be broken. And so soon after the Standard Model was invented, people began to wonder, oh, maybe even this group is just a smaller subgroup of an even bigger group, which maybe is which even represents a more unified theory at high energy. So maybe there's maybe just like the Standard Model gauge group breaks down to a subgroup at low energies, maybe the Standard Model gauge group is itself the breaking of a even larger group G. And people began to look for larger groups G that could successfully contain the Standard Model. And they found two very beautiful options. So first, One option was SU5. Well, let's say they found several very beautiful options. One option was SU5, which was found by Aj and Glashow. And then another option was SU4 times SU2 times SU2, which was found by Padi and Salam. And then both of these groups in turn can be contained in an even larger group, which is SO10, as discovered by Aj. And so what I'll be describing today is this top path. I'll be describing how the standard model can be embedded in a group in the group SU5, and how that in turn can be embedded in the group SO10. And so what we find there is that, well, by the time we get up to SU5, we've unified all of the forces of nature. What down here with the standard model, it looks like there are three different types of fundamental forces in the standard model: the strong force, the strong force of SU3, the weak force of SU2, and the hypercharged force of U1. But the idea of grand unification is that those are actually just three different parts of a more unified SU5 force. So there's just a single fundamental force instead of three different ones. And then when we unify to SO10, we'll see that not only do we unify the forces, not only does there get to be a single force, but we also completely unify the fermions. We also unify the matter in the standard model, in the sense that instead of having six different representations of standard model fermions, like in our table, in our table summarizing the standard model, the fermions lie in 6 different rows. There are 6 different irreducible representations of fermions in the standard model. But once we get up to SO10, there's just a single irreducible representation that all matter has been grouped into. And moreover, it's actually quite a striking and important representation. It's the unique spinor representation of SO10. So all of the particles get grouped into the single spinor of SO10. So that seems like I think to most people who have understood it, I think it seems too good to be just a coincidence. But exactly what the interpretation is remains open. So that's what I want to explain in broad terms. Let me say a little bit more. Let me do a little bit more specific foreshadowing. In the case of SU5, what we will see is that we will look at a particular vector space, which is the vector space of the exterior algebra in 5 complex dimensions, lambda C5. And we will see that that has a natural way that it transforms under SU5. And that when SU5 breaks down to SU3 times SU2 times U1, that this representation, lambda C5 of SU5, automatically breaks down to the representation F plus F star that I described on the previous page under the standard model gauge group SU3 times SU2 times U1. So you see there's this quite beautiful thing, which is that we at the same time as we embed the standard model gauge group with its 3 parts into a more unified group with only a single component, at the same time we take this messy representation, which has, so many 12 different bits to it, and it gets exactly combined into a single, a kind of very natural single thing, which is the exterior algebra lambda C5. The exterior algebra in 5 complex dimensions. Okay, and then for SO10, we'll see that when we embed SU5 in SO10, that so when we embed SU5 in turn in SO10, we'll see how lambda C5 precisely gets combined into a single irreducible representation, namely the Dirac spinor. So this was our representation of lambda C, of SU5, but then it becomes a single irreducible representation of SO10. Anyway, that's the story that I want to explain now in brief. So let's do it. Any questions before I proceed?
Excuse me.
Yes.
Even in supersymmetric theory, they treat both the force and matter fields on the same footing, right? Is that same as anything related to SO10?
Maybe I'll have a chance to say a little bit about that at the end. I won't be discussing anything about supersymmetry in the main part of the lecture, but so I'll really be describing the real success in grand unification is the part of it that works best is how it unifies, the fermions with themselves. It takes the 6 different irreducible representations of the fermions with all of their weird charges and unifies them into a single representation with a much more natural interpretation.
Okay.
And then because of some experimental problems that the original ideas about grand unification ran into, people introduced the idea of supersymmetric. For various reasons, people have been interested in supersymmetric extension of the standard model and corresponding grand unified theories of that. And that is an interesting extension of the story I'll be telling today, but not directly the thing I'll be talking about. I'll have a little chance, hopefully, to say something about it at the end.
Okay.
Okay, so let's see. So the next thing let's now try to explain in more detail, a bit more detail, what I just said about SU5. So I want to introduce to you, what lambda C5 is, this exterior algebra in 5 dimensions. So let me start by reviewing a couple basic definitions about vector spaces. So first of all, I remind you that a vector space is, well, the way it works is that you have a basis, you have a basis with, let's say, m different elements in it, v1 through vm, and then the vector space, the corresponding vector space consists of all different linear combinations you can take of those m basis elements. Okay, and that's, if you have m elements in your basis, then that's an m-dimensional vector space. And then now suppose we have another vector space W, which has basis elements W1 through Wn. So it's an n-dimensional vector space. Then, 2 important operations, which I've been using before, but I haven't, it's worth pausing to define them here, is that I can take the direct sum of these 2 vector spaces. And by that, I mean the new vector space. This is a new vector space, whose basis is just the union of the previous 2 bases. So I have the new basis elements are just v1 through vm and w1 through wn. Okay, so this is an m plus n dimensional vector space that I make from the previous 2. Alternatively, I can take the tensor product of these two vector spaces. And so by this, I mean that I can take any two basis elements. I can take any pair of basis elements, a basis element from the V basis, and take its product with a basis element from the W vector space, from the W basis. And the set of all such pairs forms the basis for a new vector space, V tensor W. Okay, so that's an M times N dimensional vector space. Fine, so that's what the direct sum and direct product of vector spaces is defined to be. Now, another thing I can do is if I take my vector space V as before, I can consider, for example, I can define the two forms, the vector space of two forms over V. What is that? Well, that's where I take the basis elements that's where I take basis elements of the form VI tensor VJ minus VJ tensor VI. Okay, so it's the basis spanned, it's the vector space spanned by basis elements like that. Well, how many of those are there? Obviously, I and J have to be different here because otherwise VI VJ minus VJ VI vanishes. So here we have, there's M choose two possible ways to choose this, to choose two different elements. So we have M choose two different basis vectors. So this is an M choose two dimensional vector space. More generally, I can define the P forms over V to be the vector space spanned by P basis elements from V, where again, so I'll take, now instead of just taking a product of two vectors, VI and VJ, I'll take a product of P different basis elements from V. And again, I will anti-symmetrize them, which I'll denote by this bracket. That's just the generalization of what I've done here, where I've anti-symmetrized. Or another way to say that is that I write this anti-symmetrized product as as using wedges. Another notation for this is I'll call this VI wedge, VI2 wedge wedge VIP. So that's how this wedge product is defined, and so here this is an M choose P dimensional vector space. Okay, the vector space of P forms over V, and then the lambda of V with no exponent. This is the exterior algebra over V. This is, as a vector space, this is just the sum of the zero forms plus the one forms plus the two forms, etc., all the way up to the highest forms I can make, which are the M forms, because V is a M-dimensional vector space. And so if you check what dimension this vector space has, it's the sum of all of these components. And you can check that its dimension is, it's a 2 to the M dimensional vector space. Okay, so that's what the exterior algebra over V, that's how its vector space is defined. And what I will be talking about for SU5 unification is a particular example of this, the case where V is equal to C5. So in other words, this is just the vector space where the vectors have 5 components, each of which is a complex number. Okay, that's what my vector space V is. So it's a 5 complex dimensional vector space. And what we'll be saying is that the vector space lambda C5, this exterior algebra over C5, which is a 32-dimensional vector space, what I want to show is that, okay, first of all, it has a natural way that it transforms under SU5. And that then, when I when we reduce, when we restrict SU5 to its subgroup, SU3 times SU2 times U1, when we restrict it to the standard model subgroup, that this vector space, with its transformation properties, restricts to the standard model vector space, the vector space of a single generation of standard model fermions that we wrote down on the first slide. Okay. Okay, so how does that work? Well, first of all, so as I mentioned before, lambda C5 is just the direct sum of several components. It's the 0 forms plus the 1 forms in 5 dimensions plus the 2 forms 5 dimensions plus the 3 forms plus the 4 forms plus the 5 forms. Okay, and again, the dimension of lambda p of C5 is 5 choose p. Okay, so if we label the dimensions of each of these component vector spaces, this is 1-dimensional, and then plus 5-dimensional, and then plus 5 choose 2 is 10, so this is 10. And then we have another 10 here. 5 choose 3 is 10. 5 choose 4 is 5 again. And 5 choose 5 is 1. Okay, so those are the dimensions of the component vector spaces. And now, okay, so we're dealing with the group SU5, okay, which is the group of an element of SU5 is a 5 by 5 complex matrix, U5, with 2 properties. The property that it's unitary, so it's U5 is equal to U5 inverse. U5 dagger is equal to U5 inverse, and it has determinant 1. Okay, so obviously this matrix U5 acts in a natural way on C5, on the 5-dimensional vector space. You know, it's just the usual matrix action of a 5 by 5 matrix on a 5-component vector. So yeah, if we have an element of this vector space, it just transforms to U5 V. And so in particular, the 5 basis elements here, which are also the 5 basis elements of lambda 1 C5, because really, you know, C5 and lambda 1 C5 are the same thing. They have a natural transformation law under U5, obviously. But then, since all of these other bases, you know, for example, since the basis for lambda 2 C5 is just tensor products of basis elements of C5, tensor products of 2 basis elements of C5, you know, obviously, if we know how each of the basis elements transforms, then we also know how a tensor product of basis elements like this transforms. You know, it transforms something like so it induces this transformation law for the basis elements of C5 induces a transformation law on all of the bases of the P forms over C5. And so in particular, each of these turn out to give to transform like one of the irreducible representations of SU5. This representation is what physicists call the 1, which is the trivial representation. This is the fundamental representation, or the 5. This is the representation called the 10. Now, the remaining 3 representations are just the complex conjugates of their corresponding of the first 3. So this is the 10 bar. This is nothing but the complex conjugate of the 10. This is the 5 bar, nothing but the complex conjugate of this representation. And this is, well, 1 is the trivial representation, so its complex conjugate is also trivial. It doesn't do anything. More generally, there is this useful fact, which is that you can. So if you use these 2 facts, if you use these 2 facts about unitary matrices, that U dagger is equal to U inverse, and that the determinant of U, of special unitary matrices, that U dagger is the inverse of U, and that the determinant of U is equal to 1, then you can show that the vector space of P forms in C5, or in general in C M, let's say. It's not just restricted to the SU5 case, it's for arbitrary SUM, that the vector space of P forms transforms under SUM in a way so that if we take the complex conjugate of that representation, that is equal to the representation under which M minus P forms transform. Okay. So in other words, the fact that these guys transform as complex conjugates of each other, and these guys transform as complex conjugates of each other, and these guys transform like complex conjugates of each other, is not a coincidence. The representations always get paired up that way. That the mth representation from the beginning is the complex conjugate of the mth representation from the end in a list like this. Okay. So now, so that's how lambda C5 transforms under SU5. Now let's see how to embed the standard model gauge group into SU5 and see how this representation splits up. Maybe I'll start a new page. Okay, so we want to embed SU3 times SU2 times U1 as a subgroup in SU5. Okay, so let's say that let's take a particular element of this group. Let's call it U3, comma U2, comma alpha. So in other words, U3 is a 3x3 unitary matrix, an element of SU3, and U2 is an element of SU2, and alpha is a complex phase from U1. And we want to embed that we want to embed each element of this group inside a corresponding element U5 of SU5, a 5x5 unitary matrix, determinant 1 unitary matrix in SU5. Well, how can we do it? You see, there's not that much room available. If you think about it, you have to, in the subgroup here, since SU3 and SU2 and U1 are all products with each other, the elements of SU3 commute with the elements of SU2 and the elements of U1. They all mutually commute with each other. So if we want to fit this 2x2 unitary and this 3x3 unitary into a 5x5 matrix and have them commute, well, there's really only one way to do it. You have to put them in, if this is our 5x5 matrix, you have to put you have to put them in. Let me get myself more room here. You have to put them in. You have to put U2 in the. If you put you have to put them in basically in block diagonal form. So U2 is in the upper 2x2 block, and U3 is in the lower 2x2 block. And now we want to also fit alpha into this, the complex number alpha into this matrix somehow in a way that commutes with an arbitrary element U2 and an arbitrary element U3. And to do that, well, we better, you know, the only we don't have another 1x1 block we can stick it in, so we have to somehow fit it into this matrix in a way that commutes with what's already there. And so, well, the only thing that will commute in the upper 2x2 block with an arbitrary 2x2 unitary matrix is something proportional to the unit matrix. So we have to put in alpha here proportional to the arbitrary 2x2 unit matrix in the upper block. In other words, alpha will just be will just be an overall factor in the upper block. But let's put it in as alpha to the p. We don't know what power we want yet. And let's also, and similarly in the lower block here, we have to put it in proportional to the 3x3 unit matrix so that it commutes with U3. Okay, but now remember we need the alpha to appear as a it's an element of SU5. So the determinant of the matrix alpha. So currently alpha is represented by a diagonal 5x5 matrix whose first two components are alpha to the p and alpha to the p, and whose last three components are alpha to the q, alpha to the q, and alpha to the q. And so since we want the overall determinant to be 1, it means that p and q are not independent. So what we really want here is we want alpha to the 3 and alpha to the -2, because now, you know, if you just look at the element where U3 is and U2 are just the identity matrices, but alpha is equal to an arbitrary complex phase, now it gets mapped to the 5x5 matrix, alpha to the 3, alpha to the 3, alpha to the -2, alpha to the -2, alpha to the -2, which does indeed have determinant 1. Okay, so yeah, if that was a little bit fast, but hopefully if you think about it, you'll see that this is how you should embed the standard model gauge group into SU5. That all the other options available to you are essentially equivalent to this. So now let's see. So now we know how an element U5 restricts to an element of the standard model gauge group. And so now let's see how our vector space lambda C5, which we already knew how it transformed under elements of SU5. Now let's see how it transforms when we break up those elements in this way. Well, here I'm going to leave most of this as an exercise to the viewer, but I'll do the first couple steps here. Let's look again at our vector space. Lambda C5 is lambda 0 C5 plus lambda 1. So we have our 0 forms, 1 forms, 2 forms, 3 forms, 4 forms, and 5 forms. Okay, so let's just look at these bits one at a time and see how they break up. So here, let's start with lambda 0, C5. Well, it already transformed as the trivial one-dimensional representation under SU5. And so if it's trivial already under SU5, then when we restrict to a subgroup of SU5, obviously it still doesn't transform. So this has to become this one-dimensional representation has to become the trivial one-dimensional representation of the standard model gauge group, which in our notation from the first slide is nothing but C tensor C tensor C0. In other words, the one-dimensional representation, the trivial representation of SU3, the trivial representation of SU2, and the charge 0 representation of U1. Okay, that was easy. Let's look now at lambda 1 of C5. Well, lambda 1 is where you take the basis elements of C5, the 5 basis elements, and well, with lambda p, you have to tensor p of them together, but with lambda 1, there's no tensoring. You're just taking single basis elements. So lambda 1 of C5 is just C5, and so this is a 5-component complex vector, and it's being acted on by the matrix the block diagonal matrix that we drew on the previous page. Let me just make it a little bit clearer. Let me write it this way. So we have our 5-component complex vector, lambda C5. C5, and now it's being acted on, by the 5x5 matrix we looked at a moment ago. So just to remind you, that has a U2 up here, a U3 down here, an alpha cubed up here, and an alpha to the -2 down here. And so you'll see that when this block diagonal matrix acts on this 5-component vector, it splits it. It mixes the top 2 components and the bottom 2 components. How do the top 2 components transform? Well, they get hit by a copy of. They don't get hit by. So that the top 2 components get hit by the upper block here. So they don't get hit by an SU3 matrix. So they transform trivially under SU3. So. But they do get hit by an SU2 matrix, so they transform as a doublet under SU2. They transform as C tensor C2, and then they get hit by 3 copies of alpha here. So their U1 charge is 3. Okay, so the top 2 components transform in this way, and then the bottom 2 components, well, now they do get hit. So the bottom 3 components get hit by a copy of U3, a 3x3 unitary matrix from SU3. So they transform like a 3-dimensional representation of SU3. They don't get hit by any U2 matrix. There's no U2 matrix in the bottom block here. So they're transformed trivially under SU2. And then they get hit by -2 powers of alpha, the U1 phase. So their U1 charge is -2. Okay, and so now if you look back at if you went back to our original slide and looked at these 2 bits, this bit and this bit, you would find that they are nothing but what we called L left star, the antiparticle of the left-handed. So this is nothing but the antiparticle of the left-handed lepton doublet. That's exactly how it transforms. And this guy is nothing but D right. Okay. This transforms exactly the way the right-handed down quark transformed. Okay. So now, you would just keep going. I recommend this exercise to you. Lambda 2 C5, if you're going to work that out, it's easy exercise. So now what you're thinking out, but let me give you a couple of helpful tips to keep you from getting confused. So these are the two forms over C5, but now we've seen that C5, we've already seen that C5 breaks up. If C5 is our vector space, it breaks up into two components, V and W here, V plus W, where V is, yeah, this is V plus W. Okay, so lambda 2 of C5 will break up into lambda 2, the two forms over the vector space, which is V plus W. And now you can convince yourself that the two forms over the direct sum of two vector spaces like this can be rewritten as the two forms over V plus the two forms over W plus V tensor W. So now you just have to work out what each of those three components are. And you find that, so I'll leave it as an exercise to you. But so you get a few more bits, you get a few more pieces from working out those three components. It is helpful to use the following facts. Remember, first of all, what we said before, that lambda, the p forms in m dimensions are the complex conjugate representation of the m minus p forms in m dimensions. Also, it's useful to know you'll need to know the following famous fact from group theory, which is that although in general the representation Cn star is not equal to the representation, the n-dimensional representation, although in general the fundamental representation of SUN is not equal to its complex conjugate. In the case of SU2, the fundamental representation is equal to its complex conjugate. So C2 star is equivalent to C2. Yeah, those are all the facts you need to work out lambda, to work out this case. And then once you've worked out these first three cases, you're done, because the remaining three cases, again, are the complex conjugates of the first three cases. So in this way, you can work out, it's a little exercise, which I leave to you and highly recommend. You can work out how lambda 5 splits, lambda of C5 splits under the restriction to the standard model. And again, the punchline is that it exactly corresponds. It exactly reduces to the standard model representation that we started with on the first page, which is very elegant. And in fact, in a little bit more detail, what you should find is that, so if you define lambda even to be the space of even dimensional forms, so that's the 0 forms plus the 2 forms plus the 4 forms, and you define lambda odd to be the space of odd dimensional forms, the 1 forms plus the 3 forms plus the 5 forms, then you'll find that this is exactly lambda even of C5, and this one is exactly lambda odd of C5. Okay, so that's where I'll leave SU5. I think Shane will explain some different aspects of SU5 in his lectures, but for me, that's the punchline I wanted to mention. And I'll just treat that now as a stepping stone for SO10. But you know, I hope it's clear. There appears to be something striking going on. This appears to be some clue about the standard model that when that you can sort of fit it into a single unified gauge group, and at the same time the what looks like this weird table that we started out with gets reinterpreted as this much more natural object, nothing but the exterior algebra on which SU5 naturally acts. Okay. So now let me maybe pause there before I try to summarize how SO10 goes. I see I'm getting low on time, so I'm going to try to do that. I'll just give you the gist of it, and there's a couple key ideas and then you can kind of work out the details for yourself from there. But are there any questions about SU5? I know that was fast, obviously. As I say, the idea is just to kind of get across the idea here, and maybe enough clues to work it out on your own. And if not, then there are places you can learn more, including from my course from last year or later this year. But did anyone have any questions, or should I go ahead? Okay, I think I'll go ahead if there's no questions. So yeah, the last, oops, I misplaced my notes here. Okay, so for SO10, we're going to go one step further. So you see here with SU5, we managed to get all of the fermions in the standard model into a single object, lambda C5. And it's certainly a very natural object. The exterior algebra of forms is an object that comes up very often and naturally in both physics and mathematics. But it's not a single irreducible representation of SU5. We saw it was a sum of several different representations of SU5. 1 plus 5 plus 10 plus 10 bar plus 5 bar plus 1. And now what I want to explain is that when we go up to SO10, we do get this whole structure does condense into a single irreducible representation of SO10. And not just any representation, but the unique spinor representation of SO10. So in particular, what I really mean to say is that SO10 is not really quite the right group we should be talking about here, because the spinor is not a representation of SO10, strictly speaking. It's a so-called projective representation of SO10. What it really is it's a representation of the double cover of SO10 called spin 10. Okay, but that's a kind of a just a, in a sense, just a subtlety, which maybe we shouldn't worry too much about right now. So how does this work? It turns out once we've understood how SU5 works above, it's very easy to see how the standard model fermions fit into the spinor of SO10 as follows. So let me start by giving you, I'm going to tell you a general trick, not just a trick, a fundamental fact, which is that the exterior algebra in n complex dimensions is fundamentally related to the Dirac spinor in 2n dimensions. And so in particular, we're going to see that which again is just the double cover of SO2n. And so in particular, we're going to apply this construction to lambda C5 and see how it's related to the spinor of the irreducible representation of spin 10. Or SO10, which is the double cover of SO10. Okay, so how does it work? So if I have the vector space lambda Cn, it occurs to me to check that I'm still on, right? You guys can still hear me. I'm not just talking to the air. Are there people still there?
Yeah, I can hear you.
Okay, great. Just thought I should double check. Sounds good. Okay, good. Okay, so the idea is this. So we met this vector space lambda Cn. Now I want to define two operators on lambda Cn. Okay, so again, if we have Cn, just the n-dimensional vector space, n-dimensional complex vector space, let's call the n basis vectors for that, the n orthogonal basis vectors, E1 through En. And then we saw that the basis elements of lambda Cn were obtained by taking antisymmetric wedge products of those basis elements in all possible ways. So now I will define two operators. I'll define the creation operator, Aj star. So suppose I have an element of lambda Cn. Then the way that the creation operator Aj star acts on it by taking psi to the basis element Ej wedge psi. Sorry, I didn't mean to put a hat. I put the wedge over E by accident. So Ej wedge psi. Okay. So if lambda was if for example if psi was the two form, so e.g. if psi was the two form E1 wedge E2, then Aj would map it to the three form Ej wedge E1 wedge E2. Okay. And then the second operator that I want to introduce is the annihilation operator, Aj. So it takes an element psi. So let's to make it clear what's going on. Let me look at an element like this. Let me look at a P form E1 EI1 wedge EI2 wedge ... wedge EI sub P. Okay. So Aj will map this element to, the idea is that it goes in and it finds E sub j. If E sub j appears in this list, then it goes in there and it removes it from the list. And if it had to jump over P basis elements to get to Ej, then we put a factor of -1 to the sorry. So let me try to do a better job of writing this. So if Ej doesn't appear in the list, then Aj maps this element to 0. Okay, so this gives this is equal to 0 if Ej doesn't appear in this list, or it's equal to -1 to the k -1 E sub I1 wedge E sub I2 wedge ... wedge E sub I k -1 wedge E sub I k +1 ... wedge E sub IP. So is it clear that the idea is that if Ej does appear in this list, suppose it's the kth element in this list, so then we remove it from the list to get, we started with a P form here. When we acted on it with Aj, we got a P -1 form because we went through this list. And if Ej was the kth element in this list, we simply removed it from the list. So now we only have P -1 objects that we're wedging together on the right-hand side. And if it's the kth element in the list, we have an overall minus, we put an overall -1 to the k -1 in front of it. And the point of all of this is just that now that we've defined these two operators, you can check that they satisfy the same rules as the creation and annihilation operators for fermions. So the anti-commutator of Ai and Aj is 0, as is the anti-commutator of Ai star and Aj star. And the anti-commutator of Ai with Aj star is equal to the Kronecker delta of I and J. And so now we can define, now if we define for each element I from 1 to n, for each integer I from 1 to n, sorry, did I call the dimension of the vector space M or N here? No, I'm forgetting. N, yes, sorry. So for each integer I from 1 to n, we'll define the object gamma 2I to be I, the complex number now, I, times A, maybe I should call this J to avoid confusion. So for J going from 1 to n, we'll define gamma superscript 2J to be I times Aj, the annihilation operator, plus Aj star, the creation operator. And we'll define gamma 2J plus 1 to be Aj minus Aj star. And so in this way, we've defined elements gamma I, where I runs from 1 to 2n, and we can check that they satisfy gamma I, gamma j. Their anti-commutator is equal to -2 delta ij. So they are nothing but the Dirac gamma matrices in 2n dimensions. So these guys are the generators of the Clifford algebra. These are the what mathematicians would call the Clifford algebra in 2n dimensions, or what physicists would call the Dirac gamma matrices, which define the spinors in the Dirac equation in 2n dimensions. So what we've shown, what this shows is that lambda Cn is in fact a representation of the Clifford algebra in 2n dimensions. And it's easy to check that these operators can mix any element of this vector space into any other element, convert any element into any other element. So it's an irreducible representation of the Clifford algebra in 2n dimensions. Well, that irreducible representation has a name. It's nothing but the Dirac spinor in 2n dimensions. So this is the so we've seen that lambda Cn is promoted to the Dirac spinor representation of SO2n, or more correctly, of spin 2n. And so in particular, lambda C5 becomes the spinor of SO10. And so the idea is we start with the spinor of SO10 when we restrict to the subgroup SU5. So when we restrict from SO10 to the subgroup SU5, we restrict the spinor, which is a single irreducible representation of SO10, splits up into this object, which is a fundamental but reducible representation of SU5. And then when we further restrict SU5 to the standard model gauge group, SU3 times SU2 times U1. We've already seen that this representation further splits into exactly the standard model gauge, exactly the standard model fermion representation for a single generation F plus F star. So it looks like a very beautiful story. As I say, it seems hard to imagine that it's just purely a coincidence. However, what the correct interpretation of this striking fact about the symmetry structure of the standard model is still an open question. And so the next lecture will be about that. Will be about that, and also about in a sense, trying to go further with some of the other questions about the standard model that we haven't yet had a chance to touch with this analysis. Okay, but so I see I'm getting to the end of my time. So why don't I stop there? And if there's any final questions, I'm happy to answer them.
Professor?
Yes.
You were speaking about the spontaneous symmetry breaking of SU3 cross SU2 cross SU1 to SU3 cross E1
Yes.
at low energies. From SO10 to SU5, or the breaking of SU5 to SU3 cross SU2 cross E1, are these spontaneously broken?
That's a very good
I
question.
mean, there are some fields that the vacuum expectation value, non-zero value, and then the same way it breaks to the present case. The same breaking happens to SO2, SO10 to SU5, or SU5 to, and consequently.
That's a great question. So so in the standard model, we now know, in the sense that we have good observational evidence, that what happens is that this breaking is described, the breaking for the standard model gauge group down to the low energy unbroken subgroup that we see at low energies, occurs due to the so-called Higgs mechanism, that the Higgs doublet H, which we saw in the bottom row of our table, obtains a non-zero vacuum expectation value, and because this vacuum expectation value transforms non-trivially under some of these generators, that is what breaks the symmetry of the standard model down to this subgroup. Now, when grand unification was originally discovered in the 1970s, it was assumed that the same process broke SU5 or SO10 down to the standard model, some analogous process, but with some different Higgs field or Higgs fields. So it's assumed that there's just new Higgs fields, H prime, H double prime, etc., in these larger theories that obtain VEVs. They imagined that what was going on when they originally found these theories, when they originally found the ideas described on the previous slides, they imagined that it was just an extension of the standard model, that it was that these were other four-dimensional Yang-Mills theories, and that they broke down to the standard model just as the standard model breaks down to its low energy group. Now, that was an idea that made predictions, experimental predictions, and that part of the story has not been ruled out, but nor has it received experimental confirmation. There are various and various versions of that story have been ruled out. So let's see. I mentioned I mentioned at the beginning that there are two breaking patterns for SO10 to get down to the standard model. You get down to, you can SO10 can break down through two intermediate groups, SU5 or Patty Salam, which is SU4 times SU2 times SU2. And then and then either of these groups can in turn break down to the standard model, SU3 times SU2 times U1. So now, in the absence of supersymmetry, this path has now been experimentally ruled out. Okay, the upper path here, where SO10 breaks down through SU5 to the standard model, or forget about SO10. If you just imagine that SU5 is the big group, and there's no supersymmetry, and it breaks down to the standard model, you know, that has now been experimentally ruled out. This guy breaking down to the standard model and SO10 breaking down via this lower path has not been ruled out. That's still allowed even in the absence of supersymmetry. Meanwhile, the top path, people were, many particle physicists believed that the LHC was going to find, so when this upper path was ruled out, people realized that that you could save it. Well, even before it was ruled out, they found that there was this other version with supersymmetry, and that version was not ruled out. But then when the LHC came along, if this upper path had been right, you probably should have already seen super partners at the LHC. If low energy Susie was indeed rescuing this upper path, and we haven't seen that yet. Now there is still, in principle, some wiggle room, but I think it's, you know, experiment has not been kind to the upper path at this point, either with or without supersymmetry. The lower path, as I say, is still allowed, and I'll be talking tomorrow about a approach which is connected to the lower path. But the other thing to say is that, you know, it may be that the original interpretation that the step from here to here is exactly analogous to the step from here to here, that it's just jumping to a bigger gauge theory. You know, that may or may not actually be right. I mean, what really is clear is that at the level of group theory, there is some striking relationship between the symmetry structure of the standard model and these two larger groups. But that does not mean necessarily that the right physical interpretation is that the physics at high energies is just another thing that's directly analogous to the physics we know at low energies. It could be that there's some more subtle interpretation. And again, that's related to what I'll be talking about tomorrow. But I think really the answer is we don't know. You know, that's a long way of saying that, you know, from the standard model down to its low energy subgroup, we know at this point how that works. That's spontaneous symmetry breaking via the Higgs mechanism. Meanwhile, we have a lot of numerical evidence that there's some relationship between these groups and the standard model, which seems like it's too much to be just a coincidence. But what exactly is the right physical implementation of that relationship? Why it's the case is still nobody really knows.
Okay, and this breaking should have happened in the early universe, right?
If it is really the case that if it's the case that so again, the idea since the early 70s, the dominant idea has been that this mathematical relationship between these two groups and their representations is implemented by saying that our 4D gauge theory, the standard model, is embedded in a larger 4D gauge theory, grand unified gauge theory. If that is the case, then yes, because you can see that the coupling constants, if that's the case, then you can use the four-dimensional RG equations to see how the coupling constants of the standard model flow. They run with scale due to the renormalization group, and they in order to be embedded in a grand unified theory, they have to satisfy a certain condition, and that certain condition gets satisfied only up at high scales, at the grand unified scale, and which is so the standard model symmetry breaking takes place at something like 10 to the 2 or 10 to the 3 GeV, but whereas the grand unified scale is at this much higher 10 to the 16 GeV. And then, yes, so if this whole physical picture is right, which again, I feel unsure about, but it's possible, then yes, that spontaneous symmetry breaking, if this symmetry was ever unbroken, if the gut symmetry was ever unbroken in the early universe, then it broke at very high energy scales up at 10 to the 16 GeV, or maybe it was never restored. We don't necessarily know that the radiation dominated epoch of the early universe even extends back that far, but yeah.
And if that happened, then there should be a phase transition also, like, I mean,
yes,
from one phase to another. Earlier in Professor Shu's lecture, we were taught about dynamical symmetry. So I was wondering that there should be many chain, right? We should try, if there is a phase transition, then domain wall and dynamical symmetries. Can you say some words in this direction, or something related? Is something related with the dynamical symmetries of? I mean,
yeah.
we have now symmetry, right? SU3 cross E1 symmetry. Then there is a chain to go SO10. Maybe there are several chains, right?
Right.
Then,
one
then
thing,
everything should be associated with different Hamiltonian or different vacuum expectation values, different ground states.
Mm-hmm.
So we have the evidence of CMB temperature, or at least we can get how much data and then fit to any chain, trace back to the past or something like that.
Yes. Well, one important point in that regard is that, one important point in that regard is that back when grand unification was invented, in the 1970s, that was before the idea of inflation had been invented in cosmology. And so back then, people imagined that the radiation-dominated universe, radiation domination extended all the way back to the Big Bang. And in that case, as you say, there would have been, as the universe cooled through this temperature, started at super high temperatures and then cooled through this temperature of 10 to the 16 GeV, there would have been a phase transition from the grand unified group down to the standard model gauge group. And topological defects would have formed. So you would not necessarily get domain walls, but you can show that you would necessarily get magnetic monopoles forming from that phase transition. And indeed, if it was really just the radiation-dominated epoch that cooled, you would get roughly, you can estimate that you would get roughly one magnetic monopole per horizon volume at that time of the phase transition. And so you can estimate how many magnetic monopoles you would have in our horizon volume today, which is much larger in co-moving terms, and it would be tons, so there's many of the horizon volumes at that time fit inside, our horizon volume today. So it would be predicting that the universe is full of tons of these magnetic monopoles, each of which is quite heavy, each of which is of order, would have a mass of order this scale. And that's completely at conflict with observations. If that had been the case, the universe would have collapsed to a big crunch long ago. So that was a big cosmological problem. That was a cosmological puzzle pointed out by John Preskill when he was a grad student in the 1970s. And that was one of the motivations for inflation when it was originally proposed in the early 80s to solve that problem. That if you imagine that inflation took place after the gut phase transition, or at energy scales below the gut phase transition, then even if magnetic monopoles did form at the phase transition, when the universe underwent accelerated expansion, they would be diluted. If there was enough expansion, they would be sufficiently diluted to not conflict with the observed properties of the universe today. So that's all to say that whether these early phase transitions have observational effects today in terms of the defects that they form can depend on what the cosmological history is. And in particular, inflation, if it's right, has an unfortunate way of, well, fortunate for matching observations, but unfortunate for observational predictions. It has an unfortunate way of erasing the history of the earlier phase transition if it took place above the energy scale of inflation. Meanwhile, we know that inflation could not have taken place at energy scales above the gut energy scale, because then it would produce gravitational waves in excess of the observational bounds that we have from the cosmic microwave background. So it would have had to be so inflation, if a gut phase transition did take place and inflation did take place, then inflation took place after the gut phase transition and probably wiped out evidence for it.
Yes.
Hello.
Thank you, Professor. Thank you so much.
Yes, no problem. Yes.
Basically, questions that in standard model, why massless particles become chargeless? Is there any physical reason?
Why are massless particles not charged in the standard model?
Yes.
Is that the question?
Yes, yes.
So let's see. So I think the only massless particle in the standard model are the gauge bosons, the photon and the gluons. And the gluons actually do have SU3 charge. In general, gauge bosons gauge bosons can be massless and still have charge. They can transform in the adjoint. They always transform in the adjoint of whatever gauge group they transform in. But maybe you mean
electrical charge. I'll talk about some electrical charge.
Yes, it's true that none of the gauge bosons in the standard model have electric charge. That's true. None of the massless ones do.
Right. Any reason?
And then I know that I think that, I remember, let's see, I might not be the best person to answer this. I remember, I know that there are puzzles associated with charged massless particles that in quantum field theory. So for example, there's this famous Coleman-Weinberg paper from the 1970s, which considers a theory that at tree level appears to be a theory of massless charged particles, and finds that due to one loop corrections, they obtain they do obtain a mass due to this so-called Coleman-Weinberg mechanism and dimensional transmutation. So I think there is something which quantum field theorists have found, which I mean, I remember with that Coleman-Weinberg paper that they were sort of speculating there that they referred in that paper, and then they also referred to some earlier papers that seemed to kind of give evidence that quantum field theory didn't like massless charged particles and tended to make them get a mass. But I don't, if there's a fundamental reason why that has to be true, I personally don't know what it is.
And another question is, can standard model predict the non-vanishing electric dipole moment of the neutron?
That's a good question. So yes, in principle it could. In fact, there's the famous problem called the strong.
And is there? Yes, let me. I mean, can you explain briefly?
Yes. So there is a term here. Let me start a new page here. Hopefully, I'll get a chance to mention this a little bit more in the next lecture. Actually, so in the first lecture, we had all these. We wrote down all of the fields that can appear in the standard model and how they transform. And then I said that the standard model Lagrangian is nothing but the most general formula you can write down that is invariant, that is built from all of those fields, and that's invariant under all of the relevant symmetries. And when you do that, you find that if you write down all of the renormalizable terms you can think of, you get 20-something terms, and each of which is sort of independently invariant, and so each of which can have an independent coefficient, an independent real number appearing in front of it, and so you get 20-something real numbers appearing as sort of free parameters in the standard model Lagrangian. Now, one of those terms you can write down would be a term like theta times the gauge. So G mu, if you take G mu nu, which is the, so we had G mu, which was the strong gauge field, the SU3 gauge field. So you can define a corresponding field strength, which is like G mu nu is defined to be, with two indices, is defined to be partial mu G nu minus partial nu G mu, and then minus the commutator of G mu and G nu. And then you can form a term in the Lagrangian which looks like G mu nu G rho sigma contracted with the totally antisymmetric tensor mu nu rho sigma. So this thing, and then take the trace. So this thing now is both Lorentz invariant and gauge invariant, and so you can put an arbitrary coefficient theta in front of that and add it to the action. And if this term is present, if theta was non-zero, this term would, it turns out, would lead to a non-zero electric dipole moment for the neutron. And but then when we look experimentally for the electric dipole moment for the neutron, we don't detect it. So the experimental upper bound on the electric dipole moment for the neutron implies an upper bound on this dimensionless coefficient theta, that theta has to be less than about 10 to the minus 9. And that's a puzzle. Why is that? Why is this coefficient so small, or maybe zero? That's called the strong CP problem. Tomorrow I will talk about how the exceptional Jordan algebra relates to SO10 Grand unification, but it also relates to this model, an interesting model that's been discussed in recent years by Hall and Harigaya, that gives a nice solution to this problem. So yeah, in the standard model in general could produce an electric dipole moment for the neutron, and in fact the puzzle is why it doesn't. And that strong CP problem is one of the things which is elegantly addressed by this model, which I'll talk about tomorrow.
Okay, thanks.
Are you going to talk about the neutrinos a little bit?
Oh, sorry, I couldn't hear that. Say that one more time.
Oh, I said, are you going to talk about neutrinos a bit tomorrow?
Yes, I will. I will a bit. What did you? Was there anything in particular you had in mind?
No, I don't have anything in mind because anything specific in mind I don't have. But this SU3 cross SU2 cross U1 is not being able to explain this thing. Neither any of these extensions you are talking about, they can really, I mean, address this issue, right?
Yes. Oh, yes, indeed. So so I will talk about that a little bit tomorrow.
Little
You know,
bit.
a little bit. Yeah. So you know, maybe just to say something now. I mean, so in the standard model, in fact, maybe there's something I probably should have said earlier, which I think I forgot
Yeah, last
to say.
week there was a paper by R.N. Mahapatra group
Oh, so,
on this.
I
Yeah,
couldn't hear
possibly.
what I couldn't hear what you said. Say that one more time.
Yeah, I said last week there is a paper by R.N. Mahapatra and group on this neutron mass issue.
Oh, okay.
R.N. Mahapatra. Yeah.
Is it?
We can discuss tomorrow. I mean,
Okay.
like,
So yes, I'm trying. Maybe if you sounds good.
Yeah.
Sounds good. Okay.
So, participants, I would like to thank Professor Latham for such a nice talk. Actually, this is the one, and we were supposed to request you for one more talk day after, but possibly it will be too much for you. So, like, if the participants, you want to ask any more question, or otherwise, I mean, he's talking for quite a long time. So, if you don't
Yeah, I
have a
apologize.
question,
I keep running over.
I'd like to.
Professor,
Shumi,
can I suggest?
you want to ask something? Shumi?
Yes. Professor, can you suggest us some reading material on grand unification, SO10 and SO5?
Yes, actually, there is a fantastic article
Any
by
book?
the thing I recommend is an article by Baez, John Baez,
Can you please write it in the
and
chat? Yeah, you are writing it here. Okay.
And Huerta, his student, by Baez and Huerta. It's from let me see, what's the name of that article? Well, if you look up those two authors, they have a review article from probably 2014 or something. I forget the year, but it's maybe more than 5 years old now. It's called it might be called like the mathematics of grand unification or something like that. Something like that. It shouldn't be too hard to find. They only have a few papers together. And it's a really great review article. I mean, in general, more generally, let me take the opportunity to say, if you ever can read an article by this guy, John Baez, he is a very interesting guy. He knows about everything, and he somehow has an incredible ability to write review articles that are very lucid and helpful. So this is a good opportunity this is a good example.
Thank you.
Okay.
Yeah, I think we can stop for today, Professor Latham.
Yeah. Okay, sure. Sounds good. See you tomorrow.
Yeah.
Bye.
So we see you tomorrow at the same time, 6 o'clock
Yes.
Indian Standard Time.
Very good. See you tomorrow.
Okay, thank you. Thank you so much.
Bye. Thank you.
Yeah, Professor Chakraborty has to leave because he has some other meeting to attend. He has left you a message in the chat box.
Oh, okay. Yes, yes. He mentioned that before. No problem.
Yeah, so he is not around. So we will see you again tomorrow at 6 p.m.
Yep.
Okay.
See you tomorrow. Bye.
But then bye. Thank you so much.